the last chapter, we studied levels of organization. One of them was population. Now we're going to study the properties of population. Here it says understanding of population. The human population in 1996 was 6 billion, 3 times more or bigger than the last time having counted in 1900. It says this growth between how many years? 96 years. The growth was exponentially a lot. Okay, it was a big growth, like in 1900 to 1996, and the population get bigger by a third of its size. There's a lot of people growing. So a lot of people growing, that means more consumption of resources, more destruction of the environment, That's me taking resources from the other organisms and letting them to cease to exist, or let the population grow smaller and smaller. So the human population, is it going to grow more and more? Is it going to cease to exist, or we're going to grow and let other populations cease to exist and let their species get or population get smaller and smaller? So these answers, we're going to know it once we study the properties of population. To remember what's population and definition of population, is a group of organisms that belong to the same species and live in the same particular place at the same time. We all know this. We studied it in the levels of organization and ecology. So the first property of population is population size. What's population size? The population size is the number of individuals it contains. Okay, we have a population. How many individuals it contains? 1, 2, 3, 4, 5. That's the population size. Okay, we have 2 methods for counting the population size. The first one, when it is a tidy place or an organized organisms that live in the same place, we're gonna count them. That's easy for us. But if they weren't like organized, what we're gonna do? We're gonna use assumption, okay, or estimation. Okay, so the first one was counting individuals, okay. The second method is by estimation. We're gonna estimate a number of individual or population, let's say in a square kilometer, okay. Let's say we have 10 kilometers square, like this area, okay. Let's say this one is a 10 square kilometer or 10 kilometers square. How are we going to count this? We're going to take only 1 kilometer, okay, and count them, okay. After we counted them, we're going to divide them by 10, okay, by 10. So in 1 kilometer, let's say they were 20 individuals in a kilometer square. How many individuals in a 10 kilometer square? So you're going to say 10 by 20, 2 zeros, 1, 2. That's mean 200 organisms in that 10 square kilometer. And that's the population size. Remember, we have 2 methods for counting them. Counting individual like normally, and estimation. After the property of population size, we have population density and dispersion. What's population density? Population density measures how crowded the population is. If you remember, population size is the number of individuals in it, like 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the population size. But how crowded is it? Like we're going to say, how many organisms are in a unit, okay? How many organisms are in a unit area or in the volume, okay? Let's say you have this volume or you have this volume. How many organisms are in that volume or in that unit area? So what's population density? Population density measures how crowded the population is, okay? It's always expressed as the number. I told you how it's expressed. It's the number of individuals per unit of area or volume. The number of individuals per unit area or volume. Okay, let's take an example. If we take an example here to take out the number of individuals and also the size of population and the density of population. How are we going to take it out? Let's say we're gonna square it down, okay, like that. It must be an even, okay? It must be even lines, so it's accurate. Okay, let's say there are 25 or 50 organisms here, okay? The density of this population is 15 units, okay? 15 units in an area. 50 organisms in this area, okay? That's the population density. If you want the population size, we're gonna multiply this number by, let's see how many squares we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we're going to say 15 by 20. Okay? 0 comes down. 2 times 20, 30. So 300. We can say there's 300 individuals in this area. But I told you this is only an example. Okay? This is not the accurate number. Like we didn't count them. Okay? We must count them, and it will be more accurate. Of course, it won't be accurate. This is an estimation of the numbers. Okay? This is the estimation of the numbers. And it gave us an example. It says, for example, the population density of humans in the United States, about 30 people per square kilometer. Okay, we can say the population density in Kurdistan is, let's say, 12 people per square kilometer. Another population property is dispersion. What's dispersion? What is Shewazi Balabunawa? Dispersion is the spatial distribution of individuals within the population. Shewazi Balabunawa organism lana population. Okay, we have three Shewas. We have three types of dispersion of distribution. Okay, the first one is clumped distribution, and the second one is even distribution, and the third one, individual husband. No, the third one is random distribution. Okay, so the clumped one. Okay, in the clumped one, individuals are clustered together like that. It's clustered like that. Okay. In the even distribution, individuals are separated by fairly constant. Okay, consistent. How? Like that. Okay, this is an even distribution. In the random one, it is in its name, random, like that. Okay, in the random one, each individual is independent of the location of the individuals in the population, of other individuals in the population. Okay, each one is independent. So, how does this happen, or why these three patterns happen? The first one, clumped distribution, often occur because of the resources such as food or living space are clumped. Okay, because resources such as food or living space is clumped. Okay, are clumped. Also, may be because of species social behavior. Okay, so we have two reasons: resources clumped, species social behavior. The cause of clumped distribution. Okay, we have even distribution. Even distribution happens because of social interactions. Okay, even distribution happens because of social interaction. And the last one is random distribution happens because of the wind or the birds when they disperse the seed of the plants randomly. Okay, like a wind come blow some seeds and put it in some place. That's a random distribution. Okay, it's not accurate. So a random distribution results from seed dispersion by the wind or by birds. Okay, by the wind or by birds. Look at this figure. This is a clumped distribution. This is an even distribution. Look how they are even. Okay, and this is random. Okay, if you see the clumped one, they are clumped on each other. Okay, know each type of dispersion and why and the cause of it. Okay. Population dynamics. population dynamics, it says all the population are dynamic, they change over time. So we need the information more than the size and density and dispersion to know these changes. Okay? We have an important measure in population dynamics, it's birth rate. What's birth rate? The number of births occurring in a period of time. Against it we have the death rate or mortality rate. Mortality rate is the number of deaths in a period of time. Okay? The numbers of individuals being born in a period of time, the number of individuals getting dead in a period of time. Okay? So the difference between them, birth rate, the number of births in a period of time, death rate is the number of deaths in a period of time. It's easy, there's no science in it. Life expectancy is how long an average individual is expected to live. Like how much we are expected to live. Let's say the humans in this period of time are expected to live between 60 to 70 years. That's life expectancy. Age structure. The distribution of individual among different ages in a population is called age structure. You see a population, like example of you when you are in a class, each of you has a different age. This is called age structure. The difference of ages in a population, the distribution of different ages in a population, this is called age structure. وقتا جیاوازی تمنکان لناو population اقدر جیاوازی بلا بنوی جیاوازی تمنکان لناو population اقدر. On the population we have a population that there's a lot of ages in it. Okay, when we want to count these ages, the topic will be age structure. Okay. Age structure 15, 16, 25, 13, 15, okay, 17. All these are age structure. Patterns of mortality. Mortality, remember, it means death. Okay, mortality, it means death. So the mortality rate data. In the mortality rate data, in science, okay, we can make something called survivorship curve. What's survivorship curve? What a curve رجع survival, okay? Curvy رجع survival. Survivorship curve because they show the likelihood of survival. Our organism, survival, okay? At different ages throughout the lifetime of the organism. It shows the likelihood of survival. Shows the likelihood of survival at different ages throughout the lifetime of organism. It gave us an example here. In this example, okay, the survival rate is high, it's at 100. And as the organism gets older, the survival hood or the survival curve gets lower and lower. Okay, that's mean the survival or the likelihood of survival is getting lower. That's why the survival curve is getting lower. Bonamuna it gave us an example of human at the slide. It says when the humans are born till the late ages, the survival hood is slightly high. Okay, but as they age, like let's say 15, 16, 17, 18, the survival hood rate or survival curve gets lower because of the sicknesses and or other stuff. It gave us another example. It says the survivorship curve doesn't change for the birth. Okay, this was humans. I want you to know it. Okay, I want you to know this curve. It's called the type 1. Okay, the type 1 survivorship curve. It's about human. Okay, the second type, it's about the birds. Okay, it says the life as the survivorship curve life is as a linear. Okay, it doesn't change. The survival hood is high at the beginning, and after they age, they go down. The survivorship hood go down. So the third one is called type 3. If an individual survives early period, however, it has a good chance of surviving at all ages. This type of survivorship is called curve is called type 3. If an individual survives the first ages, okay, the first years of its age or the first period of its age, the likelihood of survivorship of him is higher when he gets older, and this is type 3. I want you to know the type 1 that's about the human, okay? And the type 2 is also easy, you know it, there's no science. Okay, that was survivorship curve, okay? The survivorship curve is extracted from the mortality rate data رجعت من بشر. Population regulations, okay? We have two types of limiting factor, okay? What's a limiting factor? Limiting factor is a factor that controls population size. وأتوقع factor أنوال بومان ديالك كا population رجعي سيادتك تأخذ رجعي نزم دكت بس إجمالي individual لكنها, okay? So what are the two factors? Density independent factor. وأتا نبستراوة وب density, okay? And density dependent factor. وأتا بستراوة وب density, okay? What's density dependent factor? Such as weather, food, fire, reduce the population by the same proportion, okay, regardless of the population size. Wata population size bar hazarbi, bar pensbi, bar sadbitan, okay, they reduce the population size by proportion regardless of the population size. One weather كشوالك صار بيتن جمارين individual كان pensbitan, dehbitan, hazarbitan. همان تأثير فيها, okay? همان should go floods, fires. Balan, density dependent factor, it depends on the population size. How? Include resources limitation, such as shortage of food or nesting. بونمنا nesting أكيد والجرين. أجل nesting والجرين. أجل جماري population أكان. If the number of individuals in the population are low, okay? The nesting sites will be more for them, okay? There will be more spaces for nesting. And also for food as well. If the number of individuals are low, okay, the food shortage won't be high. But if the number of individuals are a lot, the shortage of food will be high, okay? That's density independent factor and density independent factor and density dependent factor. So we have something called carrying capacity. What's carrying capacity? Is the maximum number, okay, that a place can carry for the numbers of individuals. Let's say a class, okay? So we can say a class has 25 seats, right? But if you want to put a lot of students in one class, we can like put 40, okay? That's called carrying capacity. It can be capacitated, okay? But after 40, we have no more space, okay? We can't go beyond the capacity, carrying capacity. That means we can make it 50, 60, okay? That's the same for a place or an area. Individual in ecosystem support with the number of individuals it can support in an ecosystem, okay? By the resources like nesting, like the food. So this is carrying capacity. That means the maximum number of individual and ecosystem can support, and after carrying capacity, the number can't get more, or that population will cease to exist or can't live properly, which prevents unlimited growth of population. Like if they weren't carrying capacity, the number of population will go more and more and more. But because of the resources, they can't grow a lot. There's regulations because of the carrying capacity.